Hello, my name's Harvey, and today I'll be talking about unsupervised self-recording of obstructive sleep apnea, using a variety of different sensors. This research was undertaken as part of the Sheffield Shaw research scheme. The alternative title for this presentation is Learn from My Mistakes, because I made many of them, and there are certainly things that can be learned, and I have learned from them. So, first of all, in this presentation we'll cover a brief overview of the project. A more detailed overview is available at a previous video I made, which I'll link in the description. Then we'll cover the sensors that we used in more detail and why we used them, along with the challenges they posed, along with other challenges that we faced, and general conclusions from my experience of this project. So, a brief overview of the project. The primary aim was to create a system that people could use to self-diagnose obstructive sleep apnea, which is a condition that occurs during sleep when narrowing of the throat causes a blockage that restricts oxygen and restricts inhalation, leading to a decrease in the amount of oxygen reaching the brain, and this causes the sufferer to wake from deep sleep. And so you end up sleeping awfully fitfully during the night, not getting very good night's sleep, and feel exhausted the next day. So our main aim was to create a system that people could use to test themselves that was both affordable and unintrusive. It needed to be accessible by the vast majority of people who aren't sure whether they do or do not have sleep apnea and simply want to check. So we used the smartphone microphone and the smartphone itself to tie everything together, along with some motion sensors and a pulse oximeter, but we'll go into more detail on those later. The research question was, are we able to automate classification? Can we automatically diagnose or detect when apneic events are occurring, using the data from these, and particularly, how effective are these devices for that purpose, both when they're used by themselves versus when they are combined together. So, the entire project had to be completed within a 6-week time frame, including R&D and data collection and drawing conclusions and analysing that data. To simply connect to all of the different devices and draw them into one application took 2 of those weeks. So things were very rushed. And to some degree that explains a lot of the challenges that I faced later, but certainly many of those challenges could have been mitigated through proper consideration, as we'll discuss later. This calibration thing on the right-hand side as well, we'll discuss that, because I find that quite amusing. Originally the plan was to upload data whilst recording takes place, overnight, to a secure server, such that there's no need for gigabytes and gigabytes of audio, which has to be uncompressed, so it is quite large file sizes, to be saved on the device themselves. Due to time constraints, this never happened. So instead we kept data on the phone, which luckily at about a few hundred megabytes per night, there was sufficient free space on the phone's internal storage to store everything and then offload a few nights later. This is in the works, potentially in the future, to stream things directly to a server so that you don't end up using the entirety of your phone's storage just to record your own snoring. So the data collection process, as a result, was very rushed. Each black dot here represents a single person. So as you can see, there were only 7 people in total involved, or at least data from 7 people was used in the study. We were able to find 1 severely apneic candidate, from whom we recorded 4 nights of data. That being audio, sleep sound audio, as well as pulse oximetry, but as we'll discuss later, we weren't able to record any useful motion data. The data we collected firsthand was from our single apneic subject, over on the left, and from 2 normal, healthy, non-snoring subjects. And so the population data we had was really not representative of the global population, in that we didn't have anyone who snored but wasn't suffering from obstructive sleep apnea. And so the 4 data points in the center here were taken from a previously conducted study to develop a snoring sounds classifier, which is also made use of in this project. But as such, we weren't able to record pulse oximetry from them, so the amount of pulse oximetry data in particular is quite limited. The data that we do have, however, we were able to produce some interesting graphs. On the right-hand side, those lovely spinning things, which are at a rather low frame rate right now, they show... The top one shows the pulse oximetry data, and the bottom one shows a combination of statistical analysis on the audio alongside the oximeter data. Particularly if you look at the left-hand graph, you can see a whole distribution that is rather easy to separate. The red circles represent samples of time from the apneic candidate, and the blue ones represent the normal, healthy, non-snoring subjects. As you can see, the variation in pretty much all of the measures here is much higher variance for the apneic candidate. And particularly the percentage of time spent snoring, which is the snore prop on the x-axis, is vastly higher on average for our apneic candidate. And as a result, this means that the data is incredibly easy to separate with almost 100% accuracy. So we could have recorded just the percentage of time spent snoring, and according to our graph on the left, that would have been very easy to separate. However, that wouldn't have been particularly accurate for several different reasons, and certainly wouldn't have scaled to a larger population. So what did we do? Well, in order to attempt to answer the question of whether we could automatically classify obstructive sleep apnea events, we trained binary decision trees, which were chosen primarily because it would allow us to see what decisions were being made in a classification. The tree here is one example of the ones that was trained, and you can see there's a whole list of things, beginning with median oxygen. The median oxygen saturation measured by the pulse oximeter, which is an incredibly, a very, very valuable measure to be able to have when oxygen is the key issue of obstructive sleep apnea. So, the main questions that answer with our classification: how much data do we need? Can we get away with recording a few minutes at a time? Or do we need an entire night? Or do we need several nights worth of data? And of the data that we can record, which of it is the most useful for classification? This is something that the binary decision tree is great at telling us, because it'll generally use the bare minimum number of decisions possible to separate the data. So we could provide it with 5 different multivariate, or 5 different variables, but it could just split on one if that split is possible. So it's a great way of getting feedback for exactly what's going on. These were our results. We're separating each line into different combinations of the sensors. You'll notice motion sensors are excluded here. More on that later. But the particular trend in terms of the first question of how much time do we need is that the more time you record, the more accurate your results are, which is generally what you'd expect. But results are still relatively impressive, at least according to this graph, with up to 95% after just a couple of minutes of recording. 95% accuracy. However, these classification results, as we discussed earlier, were taken from as small a number, as few as 3 individual people, only one of whom was an apneic sufferer. And as a result, you can't draw an awful lot of valid conclusions from this. You can see this is kind of represented by the audio alone, including healthy snorers, the green bottommost line, which has a significantly reduced accuracy as a result of its more accurate representation of the population. So, general conclusions from the project as a whole, that the infrastructure has been set up. We are able to record data and run it through our classifiers. All that has been created. And the data collection method is certainly viable for collecting data. The difficulty with this project was the short time scale and having so few participants. So our next steps will be to record a much larger number to get a more accurate representation of the population. So moving on, a little bit more detail now on the sensors that are used in this project. The ones in the picture there are the MetaMotion motion sensors, which we'll talk about in a second. First of all, why did we pick these sensors? What were we looking for? On the right, there are images of polysomnography, which, as you can see, isn't a particularly easy to set up or comfortable arrangement to sleep in. So particularly important to me were the idea of making this as comfortable and unintrusive as possible. I wanted a smartphone app that you could click, set down next to your bed, and maybe wear one or two sensors with very minimal setup required. And then additionally, low cost, because this in particular was aimed at people who don't know whether they have sleep apnea and are more likely just to casually want to find out if they have concerns about their snoring or daytime exhaustion. So having low cost is a great way of increasing accessibility from people in that situation. So first of all, the smartphone microphone. Professor Guy J. Brown and his team in previous years had developed a snoring sounds classifier using audio recorded from a large set of different snorers using iOS devices. So we were doing this on Android, but I was able to reintegrate and I was able to record audio and run it through that classifier. The statistical analysis on the audio is entirely from outputs from a previously developed classifier. So having that was incredibly valuable, and it made using the smartphone microphones a pretty obvious choice. But crucially, extremely or severe apneic candidates will snore very heavily. And so being able to have audio analysis on snoring is a particular crucial part of diagnosing obstructive sleep apnea. Microphones, believe it or not, are completely non-invasive. They don't make contact at all with the skin. You can put it on a bedside table and it won't disturb your sleep whatsoever. So there's no reason not to use them in that situation. And also, with the prevalence of modern-day smartphones, absolutely zero cost. Pretty much everyone has a smartphone. So theoretically, if you could download the app onto your own phone, you'd be able to use it for no cost. And in fact, apps do exist on the Play Store and the Apple App Store that allow you to do audio analysis on your own sleep. But those are generally targeted at sleep cycle, monitoring how much sleep you are getting, rather than specifically looking for obstructive apneic events. Smartphone microphones, of course, are susceptible to background noise, and especially when we're dealing with unsupervised self-recording candidates, participants in our study, the environments are subject to sound very different from one another. So audio alone is perhaps not the most robust of measures to use, which is another good reason why we're looking at making audio analysis more robust with these other sensors. So speaking of other sensors, Ambience Lab MetaWare motion sensors were our choice for recording acceleration of the chest. At least, that was the idea. Chest movement is often recorded as part of polysomnography, but they generally do it through bands strapped around your chest. So lightweight motion sensors provide a good opportunity to remove the wires and do everything a little bit more comfortably. And of course, modern accelerometers are incredibly abundant, and also, as well as the lightweight and accuracy factors, they're also precise enough to capture chest movement. When people inhale and exhale during sleep, it's generally quite soft, but sensors nowadays have sufficient precision to capture that. These ones weren't abundantly cheap. These are about £60 or $80 US, as we got them shipped from America. But the large premium there is because of the ease of development, which is why we chose them. There's a large amount of support and documentation on their website. For a comparison, commercial accelerometers cost pence. Or, you could look at an £8 accelerometer off of Amazon. So, even if we were to use several accelerometers in a final system, it's possible we could source them ourselves and develop them from a lower level rather than relying on a high-level commercial product like this. These motion sensors also included gyroscopes and temperature sensors and light sensors, but we didn't make use of any of those, so again that would reduce the cost significantly. To record chest movement, we were able to also purchase some clips, which were very convenient for putting on collars of shirts and pajamas, and we also had an alternative solution to have it on the wrist of the user, which would make things far more difficult for recording chest movement, but it could provide useful data on whether the candidate is sleeping or not, which especially in concert with the audio analysis might help in clearing up whether a particular sound is a snore or whether it's a background noise. If the candidate is up and moving around, they're unlikely to be snoring. However, at the time of this study, the UK was experiencing the hottest summer on record for possibly since records began, and as such we had a bit of a problem because not everyone wears pajamas. Not everyone likes to wear clothes in bed, especially not when it's extremely hot. And so being able to mount these comfortably on people's chests was more of a problem than we envisioned, which contributed to the lack of data recording. And finally, the golden goose of the whole show was this SmartCare Analytics wrist-worn pulse oximeter, which was able to give us heart rate, BPM, as well as percentage blood oxygen saturation. And as we've discussed, OSA limits oxygen to the brain, and so measuring oxygen saturation is an ideal measure to look at, particularly when the graph's comparisons look like this. On the right-hand side, we have oxygen saturation. The top one is me. Whilst I was testing the device, you can see I have a median oxygen saturation of well above 95%, which is very healthy, very normal. And our severely apneic candidate had a very high variance and dropped down to as low as 75% blood oxygen, which is dangerously low. So when we're thinking about training classifiers to distinguish between apneic and non-apneic subjects, looking at the variance and the median blood oxygen saturation are clearly very good indicators. It's worth mentioning as well that this data has been smoothed with a median noise filter, as the device did drop out occasionally, but only for a very brief time, so the data here is somewhat reliably accurate. On the left-hand side there's heart rate, but there's much less of an obvious difference, so I didn't conduct too much analysis into that. Although I have read studies which say that heart rate is very useful for calculating whereabouts a person is in their sleep cycle. And so again, just like with the wrist-mounted motion sensors, that could be very useful for determining what stage of REM and whether or not a person is sleeping. So, other advantages of this particular sensor: wearable and wireless, apart from the one wire that you can see there. Certainly not uncomfortable to wear, at least for relatively short periods of time, but more on that later. And again, they provided a lot of developer access to the raw data, which was the deciding factor in choosing this over other commercial pulse oximeters. This cost about £150 for the base actual device itself, £100 for an academic license, but if we were to use this commercially, it would cost about £1,000. However, to compare with commercial, more abundant pulse oximeters, which are about £15 to £40 on Amazon, kind of shows that the technology itself is not all that expensive, and that a lot of that is research overhead and licensing. However, we didn't choose any other pulse oximeters despite being cheaper, because the access to the raw data wasn't there, and we wouldn't have been able to integrate it into one app along with the motion sensors. However, some of these do provide downloadable PDF summaries, which are quite in detail. So if you are looking for something to check your own possibility of having sleep apnea, then these things certainly aren't a bad way to start. So, those are the sensors. Next we'll move on to exactly what problems I was faced with whilst trying to work with these sensors. The motion sensors were the vast majority of the problems. Number one being that I was developing on my own personal phone, which is a OnePlus One, and the phone we gave to our test subjects was a Nexus 5, I believe. Either way, it was a different Android device. And this was a problem because it meant that our software behaved different on different devices in a very small, very specific way that was very severe. The issue was that when the subject began recording, it wouldn't work first time. They could then stop and then start again, and it would work pretty much 100% of the time after that. So I discovered a very simple workaround, and as a developer, that led me to underestimate the severity of the issue. By assuming that my candidates would reliably use the workaround, I kind of shot myself in the foot, and we lost an awful lot of data. It also didn't help that my instruction document was 4 pages long, and the instruction to use the workaround was on page 4. So, as someone who's about to use an app which seems very intuitive, you might not have an awful lot of motivation to read through this, but see if you can. Where exactly do I tell you to use the workaround? There. There's absolutely no stress. There's no bolding or importance. Oh, hang on a second. Sorry about that. There's no nothing to indicate that this is any more important than the surrounding text, which was an absolute problem. So that's certainly a lesson to be learned. Don't make your instruction documents very long. And in fact, it's very good to put feedback in the app itself, but we'll talk about that in a second as well. That caused all sorts of problems. I then integrated the workaround as a calibration, as a quote-unquote calibration, because all it was doing was starting once, stopping after 5 seconds, and then starting again. But, you know, I assumed that because I'd implemented the workaround, it would always work. However, I believe the test subject then tried to use the manual workaround after calibration had finished, and that may have broken things. So, the main takeaway lesson is that developers think very different to test participants. Test subjects will not be in the same mindset that you are when you're developing software like this. First time calibration, please wait until completed. I thought that was quite funny because it strikes me now that in the vast majority of apps you use, when you're shown first time calibration like this, chances are it's just being thrown up to distract you while a very simple workaround is implemented automatically. It's not really calibrating or diagnosing anything. But hey, who knows. So, pulse oximeter. The problems with this were much less my fault. The pulse oximeter had several battery problems, including not turning off correctly, the LED inside which measures from the fingernail, or illuminates the fingernail for measurement, wouldn't turn off despite the display turning off. So that led to various problems. I left it in a drawer over a weekend, and came back and found it absolutely dead. And then secondly, it would occasionally get frozen on charging and be completely unresponsive to all sorts of button presses. The solution was to leave it charging for about 2 hours, during which time there was no feedback to say that anything was working. So I had become convinced that the battery was completely dead, and I started taking it apart and decided maybe I'll shoot them an email, to which I got a very panicked response. I would not suggest trying to open it. So I dodged a bit of a bullet there, probably with the warranty. It was lucky that I gave up, because the battery was fine in the end. But the main takeaway is that we get problems with devices like this. Devices which aren't certified for medical diagnosis. and they include disclaimers to say as much, are potentially not going to be as widely and as thoroughly tested as actual medical certified instruments might be. A non-technical issue we found was that the finger clip of the pulse oximeter was quite tight on at least 2 of our test subjects. And even I, after testing it on the first night, woke up and found a red patch of irritated skin just beneath my fingernail, which wasn't very nice, and was sore for a while. However, having gone back on the website after this to see if they mentioned that anywhere, I scrolled down to find this. They do offer disposable finger clips, which they say should be more comfortable. So this is definitely something that we could use next time. And then our final set of problems being test participants themselves, which largely wasn't as much of a problem as it was something that I should have expected, although it would have been difficult to expect. Test participants can be quite independent. They are unlikely to just sit back and let something fail, and if they think something isn't working properly, they'll take steps to try and make it work properly. Like with our example of the apneic subject, potentially later attempting the workaround themselves, and our other non-snoring test subject, who started and stopped recording several times during the night because he didn't feel that the app was giving him enough feedback about whether it was working properly or not, and he was concerned about that. So the message here is that take advantage of your test subjects. Provide them with the resources they need to troubleshoot on their own, potentially, but more likely just provide as much feedback within the app as you can. And as an example here, this was my original design for the app, although the final thing ended up slightly different. But simply adding a spinning loading icon whilst motion sensors were connecting was enough to make me feel much more content to sit and wait. Whereas if you're looking at a blank screen, it's ambiguous as to whether or not the application is simply frozen and isn't doing anything at all. So stick in as many spinning icons as you can. Okay, so finally, some brief conclusions. Before doing this project, I was briefly obsessed with woodworking, and I sought to create a wooden PC case. The thing on the left was my prototype, made in a couple of weeks, and the thing on the right was my finished version after several months. The one on the left looks like a bit of a fire hazard, and so there's a few things we can kind of relate between that prototype and this project as a prototype for a later study. To use a woodworking phrase, measure twice and cut once. Careful consideration can certainly save distress later on. Make sure that you develop with the hardware that is actually going to be used by your test subjects. Don't assume that all Android or even iOS devices will all function exactly the same. And particularly, risk assessments are more than just pointless admin. It can be useful to force yourself to update your risk assessments as you encounter severe bugs. Because if you underestimate them to begin with, once you properly consider the likelihood of this problem occurring and the impact if it does occur, then you might just take your risks more seriously and avoid losing data like I did. The second section being prototyping. Like my fire hazard wooden PC case, prototyping is useful as it will reveal those things that you can't necessarily consider beforehand, no matter how much time you spend considering and making risk assessments. For example, developers thinking differently to test subjects is something you will struggle to think around. And so talking to people who aren't in your zone, conducting preliminary first-hand tests on people who haven't been involved with the project, and particularly in this example, sleep a mile in your participant's bed, I suppose, rather than shoes. Try it out for yourself, and like with the finger clip, you might discover that things aren't as comfortable as they may originally seem, and it could save you later hassle. A test participant after the project later tried the device, and she reported that she was finding herself squeezing the rubber clip during the night in order to alleviate the stress on her finger, which would absolutely have potentially ruined the results. So try things out for yourself so you know how to mitigate any issues with comfort. And then finally, the overall conclusion being that allowing your test subjects to take the equipment home and record themselves is certainly a viable method of collecting data, provided you include clear, concise documentation, if necessary, to stress what is necessary for them to do, and particularly give as much feedback as you can within the app whilst keeping things clear. Don't throw up pages of text, much like this conclusion screen. Just provide enough feedback that they can diagnose and be content that things are working properly. So, much like my scrappy wooden PC prototype turned into a lovely polished wooden PC after the prototyping stage was finished, hopefully in the future, as I continue to be involved with Passion for Life Healthcare and the work they're doing on studies like this, we'll end up with something much more like this than like my prototype. Thank you very much for listening. If you're interested in more of this kind of stuff, I will link the original video I made, which is much shorter than this video, it's only 5 minutes long, and gives a pretty concise overview of the project overall, as well as my report, which I wrote on the entire project. Thanks for watching, and I will see you next time.